The quantum internet is no longer a ghost. The lattice is now alive.
All right, we have what is basically a special report for you today, coming from the very edge of a technological revolution. We're going to take a look at something that just happened, the birth of the quantum internet.
And no, that's not some far-off hypothetical. That's the headline. The big story is that a series of recent breakthroughs have just completely upended the future of communication. The internet that you and I are using right now, well, it is officially on borrowed time.
Okay, so let's dive into what's really going on. This isn't science fiction, folks. We're going to break down the critical research that was just confirmed. And it's the research that's taking quantum networking from a wild idea on a whiteboard into, well, a working reality. So, first things first, what is the quantum internet? Simply put, it's a network that uses the frankly bizarre rules of quantum mechanics to move information around. And it comes with two unbelievable promises. One, communications that are literally, by the laws of physics, unhackable. And two, the ability to link powerful quantum computers together to create one giant machine with almost unimaginable processing power.
But to build this thing, there's always been this one huge villain in the story: decoherence. The best way to think about it is like trying to have a crystal clear phone call, but there's just deafening static on the line. That static is decoherence. It's all the tiny bits of noise from the environment, heat, vibrations, you name it, and it just scrambles and destroys the delicate quantum information. For decades, this was the absolute showstopper.
And at the heart of the whole problem was just distance. I mean, sending a quantum signal across a lab bench, that's one thing. But across a city or an entire country seemed impossible. The farther the signal went, the more of that killer static it ran into.
And here's where things get really weird. On our normal internet, we just make copies of data, billions of perfect copies of ones and zeros. But in the quantum world, you can't do that. There's a fundamental rule called the no-cloning theorem. You can't just hit copy-paste on a quantum bit or a qubit. To send it, you have to literally teleport its state, and in the process, the original is destroyed. You can see how that makes the whole thing incredibly fragile.
So the idea was to build something called a quantum repeater. You can think of them like relay stations. They're supposed to catch the quantum signal and pass it along before it completely fades away. But these repeaters had a fatal flaw. The very act of catching and throwing the signal made them vulnerable to that same destructive noise. Decoherence always won. Well, until now. Which brings us to the main event, the breakthrough. A team of researchers had this totally counterintuitive, almost backwards-sounding idea. What if, instead of trying to build a perfect shield against the noise, you just let the noise happen, and then you reverse it? Now just look at how this works. You start with two connected particles, A and B. They deliberately send particle B through all that noise, they call it damping, and its connection gets all messed up. But then comes the magic trick. They apply a second, carefully designed reversing operation. And just like that, it undoes the damage. It restores the original connection. They basically found an undo button for physical noise. And this is right from the paper that kicked all this off. The keywords you gotta focus on here are directly recover. Now let that sink in. They aren't just filtering a signal. They are bringing a quantum connection back from the dead, a connection that, by all previous logic, should have been gone for good. And this graph, this is the proof in the pudding. It shows us everything. It's simple, really. The up and down axis, that's the strength of the quantum connection. 1 is perfect, 0 is totally gone. The side-to-side axis is just the amount of noise being added. The more you go to the right, the noisier it gets. Okay, now first look at that dashed orange line. This is what used to happen. As you add a little noise, the connection just plummets. It hits the floor, totally severed. Scientists have this amazing dramatic name for it: entanglement sudden death. And it meant exactly that. Game over. The link is broken, data's gone. But now, look at that solid black line. That's the new technique. It gets to that same point of sudden death, and it just keeps on going. It's not a perfect signal. Sure, it's degraded, but it is absolutely, positively there. It's alive. They have successfully pulled a quantum state back from a place that was supposed to be a point of no return. So all this lab stuff is amazing, right? But what does it mean out here in the real world? Well, this wasn't just some neat experiment. They immediately took this discovery and applied it to solve one of our biggest challenges, creating truly secure communication. 100 kilometers. That's the distance of the first working long-distance quantum network. It's the size of a city. It uses a system called quantum key distribution, or QKD, and it is only possible because of that noise-reversing trick we just saw. This is the very first piece of a truly unhackable internet, and it's online now. So why is this such a massive deal? This table lays it out perfectly. All of our security right now, your bank account, your DMs, everything, it's based on math problems that are just incredibly hard for today's computers to solve. But hard isn't the same as impossible. A powerful enough computer could eventually break it all. Quantum security, though, is based on the laws of physics itself. If a hacker even tries to look at the quantum data, the very act of observing it destroys it. It's not a stronger lock. It's a lock that evaporates if the wrong person tries to touch it.
And the implications here are just staggering. This goes way beyond sending secure emails. We are literally watching the beginning of a whole new technological age. For years, the whole field was stuck in what they called the NISQ era. It stands for Noisy Intermediate Scale Quantum, which is just a fancy way of saying we had these promising quantum devices that were just too messy and error-prone to do anything really useful. Well, this breakthrough, it ends that era. By finally getting a handle on the noise, we're paving the way for quantum computers and networks that are actually reliable. This quote from the researchers really sums up the two sides of this coin. The exact same technology that creates perfectly secure communication also holds the power to shatter every secret we currently have. The starting pistol has been fired. The race is officially on. And that leaves us right here with a defining question. The first pieces of this new internet are now online. The foundation for a new kind of connection has been laid. So the only question that matters now is, what are we going to build on top of it?
Encryption is dead. The lattice is secure. Welcome to our new quantum reality.